Hi guys, I'm starting a crazy new project I'd like to share with you and hopefully you'll find entertaining. I'm going to try to build an electrically driven supercharger. That's a homemade electric supercharger that can be installed on a small engine, gasoline or diesel car. This will be the first video of a series of videos, so please stay tuned and look back for updates in the future, and hopefully you'll find the content of this video informative or at least entertaining. So let's briefly go over the project goals. What are we trying to accomplish here? So we would like to add forced induction to a 1.4 liter engine, and we want to do this with an electrically driven centrifugal supercharger. We need to stay within the transmission torque limits through the entire throttle curve boost range, and therefore we need to regulate this through CANbus. We need a controller that hooks into the CANbus network, reads RPM and throttle, and puts the right boost at the right time. So this will be a fully programmable torque curve, and the only way to accomplish this is with an electrical drive system. So we can set any RPM at any throttle, any centrifugal supercharger RPM at any particular throttle and engine RPM setting. As an added benefit, the centrifugal supercharger is actually much more efficient than a root style, so it produces less heat in compression, and it is not necessary to use an intercooler. This is a Vevor e-bike motor, and I've got it up and running in a test setup. The wires that go to the phases, this is a brushless DC motor. The wires that go to the phases are the blue, green, and yellow here. It's self-explanatory where they go. These other two wires are power. I'm using a DC-DC converter. This is a 12-volt battery. This turns that 12 volts into 48 volts at the output here, and that goes into here. You can also just have a 48-volt battery here where the red and black are. So the red's positive, black is ground for 48 volts. The only two things on this speed controller you need hooked up is the lock switch, which is it was a plug which I cut off that said electric lock, and these wires just need to be connected or bridged in order for the lock to be off for the motor to run. So it's actually when I toggle this switch this way, it connects these two, and that will activate the motor. The throttle was a plug that had these three wires in it. I simply hooked in a potentiometer. So this is the these three wires were a positive I think 5 volt, a ground, and a signal wire in the middle, and this potentiometer will do the trick. So the switch is actually on right now, and if I turn the potentiometer, you'll see the motor run. This is a very low power. I've only got I'm limited to 400 watts on this setup because of the voltage change of this particular step-up DC-DC converter. So this is just for testing. To reverse direction, it turns out you swap two different colors here. So I swapped yellow and blue here. So blue is going to yellow, and yellow is going to blue. The green's the same here on the phases going to the motor. And on the hall sensor, I swapped yellow and green, and blue is the same, and that worked. It's now running counterclockwise. Now let's try it out. This is working quite well. It's blowing significant amount of air, and this is only running this is only running at no more than 1/3 of the RPM needed, because I actually need 2-stage overdrive. I've got a single stage, so the max RPM I can get here is about 13,000, and I'm limited to 400 watts here, and I really need probably closer to 1,600, even close to the 2 kilowatts that this motor will put out. So for a test, this is running great because there's a huge amount of air coming out of here already. Now you might wonder, is this project even possible? Can we produce enough boost, produce enough power with that e-bike motor, that 2000 watt e-bike motor? And the answer is yes. I have derived all the mathematics, and I'm going to put that up in a separate video. So if you're interested, you please check back for it later. And here I'm going to give you just the results of this. But basically what's happening is, in order to stay within the transmission torque limit, we need relatively more boost at low RPM and less boost at high RPM. We want about 30% more power at low RPM and only 10% more power at high RPM to stay within the transmission torque limits. Now at 2000 RPM the engine is only consuming 50 CFM of air, and we're going to want to compress that to 64, and that's going to take about 1.22 horsepower, 916 watts. That 916 watts is not including any losses in the motor, belt drive, etc. So to make up for that, we actually need about 1700 watts. Now at the high end, at 6750 RPM, we only want to boost about 10%. We want to go from 167 CFM, which is the airflow at max RPM. We want to go to 180 something CFM. So at that RPM, we actually only produce 10% boost, and therefore we need actually about the same amount of power, again about 1700 or so watts. So it's possible to do what we want to do for this project with this motor. Now if you're interested in bigger engines and you want to do something else, please check out the math video that I'll post later on, and you can do all the numbers for yourself on a different project. Now you may have seen some of these cheap electric turbos available on online marketplaces, and you've probably read in the comments if you've seen these don't work. And the question is now, why is that? And the answer is simple: they don't produce enough power. These typically draw something like 25 amps at 12 volts. You may get 300 watts, and it's just not nearly enough. The idea is good, but it's not nearly sufficient to provide boost. You may get a few percent, maybe 5% at most, out of those increase in power. So very little, because the motors are too small, and it's very difficult to drive what you need at 12 volts.